Hello, welcome back. In the previous chapter, we discussed arrays, one of the most commonly known linear data structures in the programming world. Despite its simplicity and popularity, array by nature has a few limitations. In this section, we are going to discuss another linear data structure called linked list, which helps to overcome a few limitations. Just like a garland is made with flowers, a linked list is made up of nodes. We call every flower on this particular garland to be a node. A linked list is a very commonly used linear data structure that consists of a group of nodes in a sequence. Each node holds its data in the address of the next node, hence forming a chain-like structure. You have to start somewhere, so we give the address of the first node a special name called head. Each node is separated into two different parts. The first part holds the information of the element or node. The second piece contains the address of the next node, link, next pointer field, in this structure list. The end of the list isn't a node but rather a node that points to a null or an empty value. You might have played the game, Treasure Hunt, where each clue includes the information about the next clue. That is how the linked list operates. Each node has a data item and a pointer to another node. The power of a linked list comes from the ability to break the chain and rejoin it. For example, if you want to put an element 4 between 1 and 2, the steps would be: create a new node and allocate memory to it. Add its data value as 4. Point its next pointer to the node containing 2 as the data value. Change the next pointer of 1 to the node we just created. Doing something similar in an array would have required shifting the positions of all the subsequent elements. Let's have a look at the basic operations supported by a linked list. Insertion minus adds an element at the beginning of the list. Deletion minus deletes an element at the beginning of the list. Display minus displays the complete list. Search minus searches an element using the given key. Delete minus deletes an element using the given key. Insertion and deletion are the most expensive operation in arrays. It needs shifting of the entire elements around the place of operation. In the worst case, when the array is full, we end up copying the entire array to a bigger one to fit. Linked list makes this a little easier. We need to allocate memory for the data to be inserted by creating a node, and simply adjusting the pointer around will do the job. Thus, the linked list won itself the best choice while the total number of objects is unknown at the beginning. There are 3 different implementations of linked list available. They are: Singly linked list. Doubly linked list. Circular linked list. Let's know more about them and how they are different from each other. Whenever you think there is a possibility that a series of events must be aligned in order, we will use a single linked list. Let's take an example of a train. If you want to add a bogie, either you have to take a new bogie till the end of the train and add it, or you must spot a place in between bogies and add it. Just imagine how we are doing delete and undo operations. These operations are linked to each other perfectly, thus can do them instantly. Singly linked lists are one of the most primitive data structures you will go through. Here each node makes up a singly linked list and consists of a value and a reference to the next node, if any, in the list. A singly linked list is one in which all nodes are linked together in some sequential manner. Hence, it is also called a linear linked list. A singly linked list allows traversal of data only in one way. Clearly, it has the beginning and the end. Traversing a linked list means accessing the nodes of the list to perform some operations on them. Remember, a linked list always contains a pointer variable start which stores the address of the first node of the list. The end of the list is marked by storing null or -1 in the next field of the last node. For traversing the linked list, we also make use of another pointer variable ptr which points to the node that is currently being accessed. In this algorithm, we first initialize ptr with the address of start. So now, ptr points to the first node of the linked list. Step 2, a while loop is executed which is repeated till ptr processes the last node, that is until it encounters null. Step 3, we apply the process, for example, print, to the current node, that is, the node pointed by ptr. Step 4, we move to the next node by making the ptr variable point to the node whose address is stored in the next field. In step 1, we first check whether memory is available for the new node. If the free memory has exhausted, then an overflow message is printed. Otherwise, if a free memory cell is available, then we allocate space for the new node. Set its data part with the given val, and the next part is initialized with the address of the first node of the list, which is stored in start. Since the new node is added as the first node of the list, it will now be known as the start node, that is, the start pointer variable will now hold the address of the new _node. Overflow is a condition that occurs when a val equals null or no free memory cell is present in the system. When this condition occurs, the program must give an appropriate message. We can use the following steps to insert a new node at the end of the single linked list. Step 1. Create a new node with a given value and a new node next as null. Step 2. Check whether list is empty, head equals null. Step 3. If it is empty, then set head equals new node. Step 4. If it is not empty, then define a node pointer temp and initialize with head. Step 5. Keep moving the temp to its next node until it reaches the last node in the list, until the temp next is equal to null. Step 6. Set temp next equals new node. Underflow is a condition that occurs when we try to delete a node from a linked list that is empty. This happens when start equals null or when there are no more nodes to delete. In step 1, we first check for the underflow condition. In step 2, we take a pointer variable ptr and initialize it with start. That is, ptr now points to the first node of the linked list. In the while loop, we take another pointer variable preptor such that it always points to one node before the ptr. Once we reach the last node in the second last node, we set the next pointer of the second last node to null, so that it now becomes the new last node of the linked list. The memory of the previous last node is freed and returned to the free pool. In a singly linked list, every node has a link to its next node in the sequence. So, we can traverse from one node to another node only in one direction and we cannot traverse back. We can solve this kind of problem by using a double linked list. A doubly linked list is a data structure where each node has its data, left pointer, and right pointer. Here, each node has the address of its next node as well as its previous node, except the last node. The next pointer of the last node will point to null, which means the end of a node. Its advantage over the singly linked lists is that you will have access to the previous node. You can traverse both from left to right and vice versa. Its advantage over the singly linked lists is that you will have access to the previous node. You can traverse both from left to right and vice versa. Before we move ahead, let's have a look at important terms to understand the concept of doubly linked lists. Link minus each link of a linked list can store data called an element. Next minus each link of a linked list contains a link to the next link called next. Prev minus each link of a linked list contains a link to the previous link called prev. Linked list minus a linked list contains the connection link to the first link called first and to the last link called last. The previous pointer of the first node will always be null and the next will point to the front. If the node is inserted as the first node of the list, then we make the front and end point to this node. Else we only make a front point to this node. In step 1, we first check whether memory is available for the new node. If the free memory has exhausted, then an overflow message is printed. Otherwise, if a free memory cell is available, then we allocate space for the new node. Set its data part with the given val, and the next part is initialized with the address of the first node of the list, which is stored in start. Since the new node is added as the first node of the list, it will now be known as the start node, that is, the start pointer variable will now hold the address of new_node. We can use the following steps to insert a new node at the beginning of the double-linked list. Step 1. Create a new node with the given value and a new node previous as null. Step 2. Check whether list is empty, head = null. Step 3. If it is empty, then assign null to new node next and new node to head. Step 4. If it is not empty, then assign head to new node next and new node to head. The next pointer of the last node will always be null and prev will point to the end. If the node is inserted as the first node of the list, then we make the front and end point to this node. Else we only make the end point to this node. We can use the following steps to insert a new node at the end of the double-linked list. Step 1. Create a new node with a given value and a new node next as null. Step 2. Check whether list is empty, head = null. Step 3. If it is empty, then assign null to new node previous and new node to head. Step 4. If it is not empty, then define a node pointer temp and initialize with head. Step 5. Keep moving the temp to its next node until it reaches the last node in the list, until the temp next is equal to null. Step 6. Assign new node to temp next and temp to new node previous. In step 1 of the algorithm, we check if the linked list exists or not. If start = null, then it signifies that there are no nodes in the list and the control is transferred to the last statement of the algorithm. However, if there are nodes in the linked list, then we use a temporary pointer variable ptr that is set to point to the first node of the list. For this, we initialize ptr with start that stores the address of the first node of the list. In step 3, start is made to point to the next node in sequence, and finally, the memory occupied by ptr, initially the first node of the list, is freed and returned to the free pool. In step 2, we take a pointer variable ptr and initialize it with start. That is, ptr now points to the first node of the linked list. The while loop traverses through the list to reach the last node. Once we reach the last node, we can also access the second last node by taking its address from the prev field of the last node. To delete the last node, we simply have to set the next field of the second last node to null, so that it now becomes the new last node of the linked list. List delete, L, X. This tells us that our parameters are a doubly linked list called L, and a node called X. In the pseudo node, check if the node you want to delete is the head of your list, has no previous node. If it has a previous node, set the next node of the previous node to the next node of the node you want to delete. If it has no previous node, the node you want to delete is the head of the list. In this case, change the pointer of the head to the next node. Check if the node you want to delete has the next node. If it has the next node, set the previous node of the next node to the previous node of the node you want to delete. Circular linked list is another type of linked list data structure. In the circular linked list, we can insert elements anywhere in the list, whereas in the array we cannot insert an element anywhere in the list because it is in the contiguous memory. The circular linked list has a dynamic size, which means the memory can be allocated when it is required. You can think of circular linked list as a snake game on your phone. The circular linked list stores the x, y position of each point in the snake's body. The head of the list is the snake's head. The tail is its tail. And the nice property is that as you advance the head to a new position, the list wraps around because it is circular. This erases the tail and leaves all other body parts as they are. So you get the movement of the whole snake simply by adding a new head position. In the image above, each node points to its next node in the sequence, but the last node points to the first node in the list. The previous element stores the address of the next element, and the last element stores the address of the starting element. It forms a circular chain because the elements circularly points to each other. While traversing a circular linked list, we can begin at any node and traverse the list in any direction, forward or backward, until we reach the same node where we started. Thus, a circular linked list has no beginning and no end. We can use the following steps to insert a new node at the beginning of the circular linked list. Step 1. Create a new node with the given value. Step 2. Check whether list is empty, head equals null. Step 3. If it is empty, then set head equals new node and new node next equals head. Step 4. If it is not empty, then define a node pointer temp and initialize with head. Step 5. Keep moving the temp to its next node until it reaches the last node, until temp next equals head. Step 6. Set new node next equals head, head equals new node and temp next equals head. We can use the following steps to delete a node from the beginning of the circular linked list. Step 1. Check whether list is empty, head equals null. Step 2. If it is empty, then display list is empty. Deletion is not possible and terminate the function. Step 3. If it is not empty, then define two node pointers temp1 and temp2, and initialize both temp1 and temp2 with head. Step 4. Check whether the list is having only one node, temp1 next equals head. Step 5. If it is true, then set head equals null and delete temp1, setting empty list conditions. Step 6. If it is false, move the temp1 until it reaches the last node. Until temp1 next equals head. Step 7. Then set head equals temp2 next, temp1 next equals head and delete temp2. A circular linked list is used in personal computers, where multiple applications are running. The operating system provides a fixed time slot for all running applications, and the running applications are kept in a circular linked list until all the applications are completed. In multiplayer games, all the players are kept in a circular linked list and the pointer keeps on moving forward as a player's chance ends.